Today we are going to talk about universal hashing. Before we define universal hashing, let's just recollect what we have looked at so far. We've looked at the balls and bins framework, and we analyzed balls and bins under the assumption that each ball is thrown into a bin that is chosen uniformly at random, and the choice of bins are mutually independent of each other. And we used this balls and bins framework to analyze hashing, and we typically made the simple uniform hashing assumption. We assumed that when an item gets hashed, it's placed in a location that's chosen uniformly at random from all the possible hash locations. And using this assumption, we can invoke the ideas from the balls and bins framework. So, for example, when we look at chain hashing, the worst case performance of chain hashing correlates to the height of the most loaded bin in the balls and bins context. We also looked at independence in the last lecture. In particular, we noticed that independence is somewhat expensive, but if we relax the notion of independence from mutual independence to some k-wise independence, then it's cheaper. In particular, we looked at ways to generate pairwise independent random bits and pairwise independent random numbers. And we also noticed that while limiting ourselves to pairwise independence, we didn't lose out too much. We were still able to employ, for example, the Chebyshev's inequality. We have also observed in the past that hash functions can be expensive uh, and difficult to analyze and hard to implement and so on and so forth. And the problem comes from the fact that hash functions have to balance two requirements. On the one hand, hash functions should behave randomly. They should have good randomness properties. For example, when you hash an item, it must be equally likely to be hashed into any one of the locations. And also, we would like these hashed values to be mutually independent of each other. So that's good randomness properties. But on the other hand, when you hash an item, it has to always hash in the exact same location. So that's a very deterministic requirement. Because when you hash an item to store it, and later on when you hash the item to search and retrieve it, they must be in the same location. Otherwise, it's not going to work. And so these two requirements, the randomness requirement versus the deterministic requirement, always brings about a bit of tension for us, something that we need to resolve. And here's an idea for how to resolve this tension. Okay, now think about a single hash function. This is going to have good deterministic properties because it's a single function, so anytime you hash an item, it's always going to go to the same location. But when we choose a single item, it suffers on the randomness front because it's a single hash function. So how do we alleviate this situation? Instead of focusing on a single hash function, let's consider a family of hash functions. So we have this whole family of hash functions. When we actually need a hash function, we choose one, but we choose one uniformly at random from this entire family. So in this manner, it's easier for us to bring in the randomness requirements for hash functions. Okay, but we need to be a bit careful when we do this. So let's try to be a bit formal and let's try to define such a family with the correct properties that we require. Okay, so we're going to define what is called a universal family of hash functions, and so it's going to be such a family H, and each member of the family is a hash function that will map a universe to a set of locations. And such a family is going to be called a k-universal family of hash functions if the following condition applies. So now uh, let's say you choose a hash function h uniformly at random from this family. And let's pick x1, x2 up to xk, which is a subset of the universe. And this subset has to be of cardinality at most k. Then we will require the probability that each of the items hashed into the same locations should be at most 1 over n to the k minus 1. If this condition holds, then this family is called a k-universal family of hash functions. And remember, this condition must hold for a hash function h chosen uniformly at random. So the randomness is based on this choice of hash function. And it must hold for any subset of at most k items drawn from the universe U. And you might think this is a hard requirement, but it's actually quite easy to obtain. So let's, for example, focus on pairwise, or rather, a two universal family of hash functions. So here's one way to produce such a family. So now our universe is ranging from 0 to m minus 1, and the hash locations are ranging from 0 to n minus 1. And let's pick a prime number p that is larger than m. Okay, and let's define a hash function h with parameters a and b. This hash function will take an x. X is in the set V. We'll take an item x and hash it into the location ax plus b. First, you mod it with p, and then you mod with m. Okay. Well, that's just a single hash function. But remember, we have parameters a and b. So with by extending our choice of values for a and b, a ranging from 1 to p minus 1 and b ranging from 0 to p minus 1, we will get not just one hash function, but a family of hash functions. Okay, and this family of hash functions is a two universal family of hash functions. And we're going to skip the proof, but it suffices for us to know that this is a two universal family of hash functions. And as you can obviously see, the construction is quite straightforward. Let me just point out one minor technical detail. B ranges from 0 to p minus 1, but A only ranges from 1 to p minus 1. So if we want to generate or pick a hash function uniformly at random, we pick an A uniformly at random from 1 to p minus 1, B uniformly at random from 0 to p minus 1, and that immediately implies a choice of our hash function h a comma b, and that's our choice of hash function. We can extend our theory of universal hash functions to something that's slightly stronger. So here we're going to define what is called a strongly universal family of hash functions. It's again a family in which each member is a hash function that maps the universe to the set V. And for this family to be a strongly k-universal family of hash functions, here's the condition that must apply. Now again, as before, let's consider one of the hash functions h chosen uniformly at random. And let's assume x1 through xk is a subset of the universe, and this subset is at most of cardinality k. And now for any choice of yi's ranging from 0 to n minus 1, basically yi belongs to v. Now the probability that x1 is hashed into y1 and x2 is hashed into y2 and so on up to xk hashed into yk should be at most 1 over n to the k. My apologies, it's not at most 1 over n to the k. It should be exactly equal to 1 over n to the k. And this is the requirement of for strongly k universal family of hash functions. And quite obviously, this is a stronger definition. But the nice thing is such a family can still be constructed quite easily, especially if all we require is a strongly two universal family of hash functions. So again, how do we do that? Well, the universe, let's say, is ranging from 0 to p minus 1. And here p is a prime number. And also let's assume that v ranges from 0 to p minus 1. Again, we define each individual hash functions based on parameters a and b. So a comma b of x will take the item x and hash it into the location ax plus b mod p. Okay. And this family induced by the various choices of a and b, we can prove is a strongly two universal family of hash functions. Again, we're going to skip the proof, but it's obvious to see that this family can be easily constructed. And well, maybe the family need not be constructed. We can draw a hash function uniformly at random from this family very easily. All we need to do is draw two numbers a and b from 0 to p minus 1, and that implies the choice of the hash function. So before we proceed, let's ask ourselves some questions. I would like you to think about these questions and answer them for yourself so that you have a sense of confidence about your understanding of these this universal family of hash functions. Now let us suppose H is drawn from uniformly at random from a two universal family of hash functions. My question is H pairwise independent? Think about that. And answer the same question now under the context of drawing H uniformly at random from a strongly two universal family of hash functions. Is H now pairwise independent? What's going on here? Okay. Finally, is a strongly two universal family of hash function always also a two universal family of hash functions? Okay. Think about these three questions and make sure your understanding of universal family of hash functions is clear that way. Now we've defined these universal family of hash functions. How useful are they? For example, our first concern would be their application in a very fundamental context. For example, the balls and bins context. What happens when we replace the notion of balls choosing bins uniformly at random with the notion of balls choosing their bins based on some hash function that is drawn uniformly at random from, say, a two universal family of hash functions. Okay. So let's think about that. So we have m balls, n bins. We use a hash function h to take each ball and hash it into a particular location, a particular bin. And this h is drawn uniformly at random from a two universal family of hash functions. Okay. So what's our max load? And in order to understand that, let's define a random variable y. And that's defined as the number of balls in the max loaded bin. And obviously our question now is what is the bound, or what is the reasonable bound on y? In particular, we want to know what is the value of k for which the probability that y is at least k is bounded from above by a half. And in order to understand the probability of this event, we're going to be a bit conservative. Let's look at the bin with the k balls. Okay, there must be at least k choose two pairs of balls that collide just in that one bin. So instead of bounding the probability that y will be at least k, we will be a bit more conservative and we will bound the probability that the number of colliding pairs is at least k choose 2. But this number of colliding pairs needs to be modeled a bit carefully. For that, we're going to use an indicator random variable, xij, and that's xij is going to take the value 1 whenever ball I and ball j land in the same bin. Otherwise, it's going to take on the value 0. So xij is a very natural choice to model colliding balls. Clearly, the expectation of xij is at most 1 over n, because from our assumption that we're using h drawn uniformly at random from a two universal family of hash functions, we know that the probability with which ball I and ball j will collide is at most 1 over n. So the expectation of the Bernoulli random variable xij is going to be at most 1 over n. And of course, our interest is counting the total number of collisions. So with that being the case, we'll define uppercase X to be the summation of all these xij's. And if we look at it this way, the expectation of X is simply at most m choose 2 times 1 over n, which is at most m squared over 2n. And since we have the expectation, we can now apply Markov's inequality. And using Markov's inequality, we get probability that x is at least m squared by n is at most the probability that x is at least twice the expectation of x. This m squared by 2n, remember, is the expectation of x. And that's, of course, at most 1 by 2. So remember, our goal is to find the k such that the most loaded bin has k or more balls in it, right? So, and we've been a bit conservative in bounding that probability. In order to get our value of k, we need to set k choose 2 to be at most m squared by n, because k choose we don't want we're bounding the probability that the number of collisions is at least k choose 2, right? So of course, k choose 2, we approximate that with k squared by 2, and that leads us to the bound that k must be at least m times square root of 2 over n. And this is for an arbitrary choice of m. But if we restrict m to be exactly equal to n, we get k to be at least square root of 2 times n. This result must be viewed under the backdrop that if we use uniform and mutually independent choice of bins for each ball, then the height of the max loaded bin is going to be at most O of ln n over ln n. So this is significantly worse, but it's still very general in nature. So it's worse. It's no longer logarithmic. It's proportional to the square root of n. But we were able to get this result using a hash function drawn uniformly at random from a two universal family of hash functions. So it's in that sense very general in its application.